All right, guys, let's go ahead and get started. Today we are talking about how to interpret data tables on the USMLE, and more specifically, what to make of the confidence interval when you see it. So I'll give you a sample question right here, and you can pause it if you want to work through this. But moving on, essentially all we have to look at is we're given confidence intervals. And one thing to know about confidence intervals is if they include the number 1, then that means they're invalid. And so if we look at basically what this study is doing, we're looking at whether cocaine or tobacco use influences the relative risk of vasospastic angina. And so we're given a bunch of relative risks. And, we can read these relative risks. And one thing we can immediately point out, if we go over to the confidence interval table, what we want to do is find out which ones include 1 in the confidence interval. And so those would be this one, and this one. And what that means is that these study arms are not statistically significant. And so what we're left with is only 1 even seems to be significant. Once we can do that little thing there that takes only a few seconds, we've already ruled out multiple answer choices. And so something that just talks about cocaine use, we already scratched that out. Something that just talks about smoking, we already scratched that out. And so you can kind of go through this and look at them. But the big idea is that if 1 is included in the confidence interval, it's invalid. And so, you can either memorize that or you can kind of think about it. It has to do with something called the line of null effect. And so if a confidence interval includes 1, the results of said data are statistically insignificant. And if you think about why that is, when you're talking about things like relative risk or odds ratio or hazard ratio, when you have the relative risk just equaling 1, that basically means that your new variable is no different than the null hypothesis. And it comes down to something called forest plots. And so you can see here we have something, we have 1.0 here. If we draw a line there, this is called the line of null effect. Any data that crosses this line is insignificant. Point blank. Just literally just memorize that. And so, what test writers will do is they won't give you this very convenient plot. They'll kind of make you guess at it. And so, just like we saw in this test question, we have relative risk and we have confidence interval. And so, I pulled this up from a real study. This was just looking about risk factors related to, I think it was related to basically neonatal deaths. And so we have a couple risk factors here. And, we have the relative risk, and in the parentheses, we have the confidence interval. And so immediately, we see that this one crosses 1, this one crosses 1, this one crosses 1. And so what that means is these 3 factors were not statistically significant, and we're left with only perinatal deaths. So, this is, useful both in tests as well as real life. And so, if you have a drug rep giving you data, you want to quickly be able to say, okay, all these different tables that you've given me, because of the confidence interval, they're not significant. And so just going back to more elementary concepts, relative risk is basically the incidence in exposed group and incidence in unexposed group. And so when you think about what a relative risk of 1 means, it basically means that there is no difference between an exposure and not being exposed. So I think this makes more sense if you use an example. Let's say we're looking at the incidence of strep throat and whether going to the Super Bowl made a difference. And so if we calculate a relative risk of 1, that means that going to the Super Bowl and not going, you had no difference in your risk of getting strep throat. A confidence interval, all it is it's a way of saying I'm pretty sure my data falls somewhere in this range. And so let's say we have a mean, we're given a lower limit and an upper limit. When we say we're 95% confident, that means we're 95% confident that the mean falls somewhere in this distribution. And so one tertiary concept you might have to apply on tests is that a 95% confidence interval, it corresponds to a p-value of 0.05. And another thing you have to know is that a confidence interval gets narrower with larger sample sizes. And so this kind of makes sense because if you think about a confidence interval as being a guess, you know, the more samples you have, the better of a guess you can make, right? And so your confidence interval will get narrower. I'm not going to go too long on this slide because I want to make a separate video on it, but I want you to look at all the different ways I've written what a p-value means on the left. And so, you know, keep this in mind because they might ask for your interpretation of statistically significant data, and you might have to just plug one of these statements into it. I think this is a good thing to know for real life as well. So one thing you might be wondering, right? If a p-value of 0.05 means that there's a 5% chance my data is wrong, why not just go with a p-value of 0.01? Why not, you know, why not just be more confident? It sounds like a good idea on its surface, but what you're doing, if you look at alpha and beta here, recall that beta is the chance of a false negative. So as you get more confident in your data, you know, as you use a stricter p-value, you have a higher false negative rate. And so a smaller p-value, it means there's a higher chance of failing to detect a difference when there actually is one. So basically a smaller p-value means you have a higher possibility of a type 2 error. I think this makes more sense if you use an example. So let's say we spent, you know, $30 million developing a drug, and we wanted to see if a new biologic reduces histamine release in people with peanut allergies. By choosing a p-value of 0.01, your drug trial shows that the drug did not work any better than Benadryl. Essentially what we're saying is, you know, our drug had a p-value of 0.02. And so what that means is that at a 5%, you know, at a p-value of 0.05, your drug might have passed the trial. And so essentially the trial made a type 2 error. There actually was a difference. Your drug did work. It just failed to show a difference. And that's why we make this trade-off. It's because we want significant data, but we don't want to miss results that are actually there, just hidden. To summarize my rambling, what we're talking about is as a p-value gets smaller, your rate of false positives goes down, but your rate of false negatives goes up. And so it's, I'm just describing what the yellow arrow is showing. So two other concepts that they might ask you about. You know, a researcher is figuring out how to represent her data. She initially presented her findings with a 99% confidence interval. Her PI instead convinces her to go with a 95% confidence interval. And so would her new results be less or more accurate and less or more precise? I'll give you a second to think about this. But moving on, a narrower p-value, it gives you more precise data, but the data is potentially less accurate. And so what this corresponds to is essentially a larger sample size. So similar question, you know, let's say we gathered up some data and we found that the 95% confidence interval was 1.02 to 1.85. And so it was significant. And which p-value would correspond to this? And so this one's, you know, pretty easy. Anything less than a p-value of 0.05. So you can kind of see all the different ways how they would test this. So in summary, if you have a confidence interval that includes 1, there's a plane overhead. If you have a confidence interval that includes 1, the data is not significant. And on a forest plot, if you cross that line, your data is not significant. These two things mean the same thing. So get comfortable with these tables, get comfortable with these forest plots, and let me know if I can be of any help. Thank you, guys.